Okay. Good morning, everyone. I'm Jesus, and for the last years, I've been working together with Dyalog, trying to bring back APL to Academy. And as part of this effort, one of the things I do is to go to universities, to conferences, to talk about APL. And always, or almost always, I get some question about data science. Can I use Dyalog for data science? How could I do data science using APL? Well, this talk is my answer to all those questions. But before that, an easier question: what is data science, to set the floor? We can set the definition in Wikipedia. It's a bit long, so I remove some words. And we get that data science uses scientific computing to extract knowledge from data. What this means in practice, what most people doing data science are doing, they have a large amount of data in tables, and from that they generate smaller tables and charts so that they can interpret this data. Okay, let's see some examples. We are going to see 3 examples. The first one is a very classical example in statistics related to something that happened at Berkeley University in California in 1973. It was observed that more male applicants were being accepted in the graduate schools than female applicants. And the question is if there was gender bias at the university departments or if this was a case of the Simpsons paradox. The Simpsons paradox is a phenomenon that happens when you want to correlate two variables and you want to search a trend here. You have some data points and you can see very clearly that that's the trend we have. However, if we divide this data into categories, then we don't have that trend. We get the opposite. So the question is, was this happening at Berkeley University? Let's see. We get as input a CSV file, a text file with comma-separate values. And here we have a row for every student telling us which major they apply and their gender. We have a total of almost 13,000 lines. And the first thing we do is to load this array into APL. And then for every combination of major and gender, we calculate the number of students who were admitted and also the total number of students who applied. And now we have a much smaller table that we can work with. We calculate some totals, we add female and male to get the total for each major, and also add all the majors together to get the absolute total, okay? And everything remaining will be to calculate the percentage. We calculate the percentage of admitted students in each case, and also the percentage of students who applied to each of the majors. And this would be the solution to our problem. This is what we were searching for. To see it better, we can do some graphs. So here at the bottom left corner, we can see that indeed more male students than female students were accepted. We already knew this. But when we look at the data by major, we don't see that. Sometimes more female students, sometimes more male students, but pretty much in each department they are even. So indeed, this was a case of the Simpsons paradox. It's probably one of the most famous examples of the Simpsons paradox. And to understand it better, we can look at the percentage of applicants to each major. And then we see that what happens is that relatively many students, many male students, are applying for majors A and B, where the admission rates are quite high. And female students, for some reason, prefer majors C, D, E, and F, where admission rates are quite low. Okay, there are many interpretations about this, but we had a lot of data. We extracted some information from there, so we did some data science. And let's see how we did it. Let's look at the code. So this is the APL code. It's not much. We are going to look at it in detail. And we are going to compare it with the solution using Python and the Pandas library for the same problem. The Pandas library is probably the most popular library for data science and the one that most people learn first. So let's go. We start reading the CSV file. We use quad CSV in APL. We use panda-CSV in Python. Then to group, in Python, we use a method called group by, and then we do aggregations called sum and count. And in APL, instead of group by, we use the key operator. Instead of sum, we use plus reduce, and instead of count, we use tally. For the totals, it's pretty much the same. In Python, we use group by and sum, and we also concat to put the data together. And at the bottom, we see that we use a method called sort index to sort the table. In APL, we use again the key operator and plus reduce. We use comma and comma bar to concatenate, and we use the sorting idiom to sort the table. And then to calculate the percentage is quite simple arithmetic. We can do this in both languages too. You will have also noticed that in APL we are using the position of the columns, while in Python we are using the labels. Of course, the Python way is more convenient. The APL way makes the code a bit shorter. We could use column positions in Python too, and we will see later how we can use column labels in APL. Then we would have to do the graphs. In Pandas, the default is to use matplotlib, which is a Python library. In APL, I'm using the shiny new EWC with Apex charts. Well, you can see that we can do pretty much the same chart using EWC. I'm very happy with EWC. So this is the code for both solutions. You can find this and the rest of the code that I have in GitHub in case you want to look at it at your own pace. And let's go for another example. We are going to talk about flowers now, about iris flowers. This is an example of the iris flowers, and iris flowers have petals and sepals. And Roland Fisher, he was a British botanist, and in 1936, he measured the length and the width of the petal and sepal of 150 iris flowers and classified them in different species. And since then, this data set has traditionally been used in statistics before and in data science nowadays. And the goal here is to see if we can correlate these features that Fisher measured with the class of the flower. We are going to look at the code directly, as we did before. We are going to compare APL and Python. And the first thing we notice is that in the APL version, there are some things that are not defined yet. We will need a few statistical functions. It's very common to combine statistics and data science. And for example, for the average, everyone knows the idiom. You could use that, and you could find other things maybe in APL card, but you can see that some of them can get a bit complicated. So you could prefer to put all this in a namespace, so that is more tidy. But even then, you have to be careful. There are sometimes corner cases you have to take into account, and so on. So my recommendation would be just use timestat. We just show a presentation on timestat, and you actually have all these functions in timestat. You could do that, and it's what we do in Python using a library. We have libraries and packages too. Okay, so back to the flowers. We start as before reading the data. Then we define an operator in APL, a function in Python that is to do an aggregation for each class and also for the total. And we use this operator or this function to calculate some basic statistics, percentiles, minimum and maximum, average. We can put all this in box plots, again done with the WC. And here you can see that it looks like we have some trend with these boxes, no? So we do a full correlation analysis. I don't have much time to explain what is a correlation analysis, but what we are trying to do is to find correlation between pairs of variables. If we have numbers close to 1 there, it will mean that we have a linear relationship between those variables. And it's particularly interesting to look at the correlation with the class. If here we have numbers close to 1, that means that we have a linear relationship, and we can correlate that feature, that measurement, with the class of the flower. So we solved the problem. That's what we wanted to do. Another one done. You can find this one in GitHub too. And the last example I wanted to show, I really wanted to show some example of a time series analysis, because it's a very common problem in data science. And what I did is I used Google Trends to see the interest on Scotch during the last 5 years. We can look directly at the results, and you can see that we have peaks every Christmas, with a huge peak in 2020 during the pandemic. And we can calculate several tables, the amount per month, relative change, average, minimum and maximum per month, per year, and so on. This is the code. I won't go into it. You can see that the APL code is quite short. 1 line to read the file, 1 line to parse the data, and then key operator, key operator, key operator to make the tables. And you have this one in GitHub too. And with these examples, I think I made my point to give my answer to all these questions that I said at the beginning. If you can do data science with APL, and how do you do data science with APL? And my answer to all these questions is the same. Science, key data. So of course you can do data science in APL. You just have to put your data at the right of the key operator and your science at the left of the key operator. And we saw how using only the primitives we can solve many problems. But there is much more that we can do. There is a number of advanced features in Dyalog APL that we can use. So let's see what else we can do. For example, we could define a set of functions to work with data tables. We have an excellent example by the late Roger Hui, who presented 6 years ago in the Dyalog meeting this nice set of functions to work with inverted tables. You know that we can represent tables in different ways: matrix, list of rows, list of columns. If we have a list of columns and represent it as a list of vectors, this is what we call an inverted table. And if you are working with columnar data, this is usually a much more efficient way to deal with them than having a rank 2 array. So Roger defined this set of functions to work with them, and you can see that we have without, unique, the key operator. Index of is interesting because it's using an IBeam. And, well, I really invite you to watch the talk by Roger, which is a very good talk, and learn more about this. We could also combine this, for example, with the new features that are coming in version 20. Adam explained yesterday how we will be able to very easily create a namespace. So, for example, in this line here, we could create something very similar to a Python data frame, where we would have a namespace where we have the labels and where we can refer to the columns by their labels and operate with them. And this will be closer to what we do in Python. But if we want to be close to Python, we actually can do it now. As a proof of concept, I wrote a data namespace that tried to mimic a bit the Panda library. It's of course a toy compared with the Panda library, but it's already good enough to solve the samples that we saw before. Here we have the first sample, the one about admissions at Berkeley, and you can see that we can generate some prettier tables than before. And if we compare this with the Python version, it looks a bit more similar now. We are using the column labels to access to them. We have data series, we have data frames, we can group by, we can join these frames, and so on. You have this code in GitHub too. together with the other two examples and some very basic documentation about how to use this. But please remember that it's a proof of concept. Don't make your $35 trillion depend on this, please. And to finish, I would like to show a real application of what I'm doing. I think all these problems are very interesting, but this introductory material is what you see in Data Science 101. And I wanted to show some of the work I'm doing. I'm a material scientist working in metallurgy. And one of the things we do is to look at the steel samples in the microscope all the time. So here we have a sample of a steel which is less than 1 millimeter by 1 millimeter. And we put it in the electron microscope, and then we get a measure for more than 9 million points, and we get the orientation for each of these points, the crystallographic orientation. It doesn't mean what that is, but it's represented by the color in this graph, okay? And then we calculate the distribution function of those orientations, something called an orientation distribution function. This function would have some peaks where you have the blue colors, for example, okay? And then something particular we did in this paper we published some years ago was to divide all this data in grains of different size. A grain is a region with the same color. And then we divide them in size intervals, and we calculate an ODF for each of them. And putting all this together by some mathematical artifacts, we get a continuous function that correlates the orientations and the grain size. I guess you are a bit lost, but everything I want to explain is that this is just a data science problem. We have the data coming from the microscope. Going to the grains is some kind of aggregation, it's a group by. And then the ODF calculation is another aggregation. I'm working in the ODF calculation now. This is a bit complicated. It is still a work in progress, and don't worry, because it's a topic for another day. So instead, I'm going to finish. And I'm glad to say that I have some good news for everyone. If you are an APLer and you have been a long time using APL and you have been using APL to extract some useful information from data, congratulations, you are a data scientist. And if you are a data scientist and you are not using APL and you are using maybe Python or Julia or whatever, try APL. You are missing a great tool. We have native arrays, we have cool glyphs, we have a key operator. So it's an excellent tool for data science. And to finish, I would like to thank everyone who helped with this presentation. And well, all of you for listening. Thank you very much.